Did you know that back in the day, calibrating a transmitter meant using a screwdriver to tweak tiny potentiometers? It was a delicate process, prone to errors, drift, and time-consuming adjustments. Engineers had to manually set zero and span, adjusting tiny screws just right to get an accurate output. Fast forward to today, and things have changed completely. We now have digital calibration, where adjustments are made electronically using microprocessors without even touching the device physically. In this video, I'll explain how digital calibration works compared to the old-school zero-span method and why modern engineers prefer it. Let's start with the traditional method, zero-span calibration. This method was common in analog transmitters, which output a 4 to 20 mHz signal. Here's how it worked. Zero calibration. The technician applied a 0% input, zero pressure if it pressure transmitter, and adjusted the zero potentiometer until the output read 4 mA. Span calibration. Then, a 100% input pressure was applied, and the span potentiometer was adjusted to make the output 20 mA. Iteration needed. Adjusting one setting could affect the other, requiring repeated fine-tuning. While this method was simple, it had major drawbacks: mechanical drift over time, environmental effects, and difficulty in maintaining accuracy. Plus, every transmitter had to be calibrated manually at the site. Not exactly efficient, right? Now let's see how digital calibration revolutionized this process. In smart transmitters, everything is handled electronically using a microprocessor. Instead of manual potentiometers, we adjust digital registers through software. Here's how it works. Step 1. Analog signal conversion. The sensor measures the physical parameter, e.g., pressure, temperature. The signal is converted to a digital value using an analog to digital converter. Step 2. Zero and span correction electronically. Instead of adjusting potentiometers, the zero and span are stored in memory and adjusted using software, and every time this stored valve is subtracted from raw value. This correction is applied directly to the digital signal. No mechanical parts, no drift. Step 3. Automated linearization and compensation. Digital calibration allows multi-point calibration, not just zero and span. The microprocessor stores multiple calibration points and applies a curve-fitting algorithm for higher accuracy. Step 4. Temperature and pressure compensation. Built-in temperature sensors detect environmental changes and adjust readings automatically. Some transmitters even self-calibrate, meaning fewer field visits. So there you have it. We've seen how traditional zero-span calibration worked with manual adjustments, and how digital calibration now allows for electronic, software-driven precision. If you're an engineer working with modern transmitters, understanding digital calibration is a must. What do you think? Do you prefer the old-school hands-on approach, or do you embrace digital automation? Let me know in the comments. And if you found this video useful, don't forget to like, share, and subscribe for more engineering insights. Thanks for watching, and I'll see you in the next one.